All right. Hi, everyone. Thanks for joining us in our session today. I'm Anil Kumar. I'm a product manager at Couchbase. I work on our flagship product, Couchbase Server. Along with me, I have Dong Wong from PayPal. He's a senior member of technical staff at PayPal. So we'll be doing we'll go through the benchmark testing. Dong has done extensive testing on the XDCR technology to validate whether the XDCR is going to be the solution for their use cases, right? So we'll basically go through this entire benchmark testing. So first few minutes I'll spend talking about what is XDCR, what's the cross data center application for the people who are new to the Couchbase. I just want to give you a little bit of context, and then we'll jump on to the benchmark testing itself. Sorry. All right. All right. All right, sorry, give me 1 second. Okay. I think I introduced already. So just to give you a quick background or give you a context of what is cross data center application. This is the laser. Okay.
Yeah. There it is.
Okay.
Center.
Sure. Thanks for you. So for the people who are new to the Couchbase, so we have a cross data center application, which is in the short form we call it as XDCR. What XDCR provides you is ability to replicate data between the Couchbase clusters. So you can use the XDCR technology for disaster recovery, for availability solution. Also, if you want to have a geo distribution of your data. So if you have a cluster in the East Coast and you have a cluster on the West Coast, you want to basically bring the data closer to the user, you can basically use cross data center application to like geo distribute the data, right? So in simple terms, like what XDCR provides you is like the replication of the data between the clusters. It's very easy to set up. Essentially, it is like a two-step process if you want to set up the XDCR cross data center application. If you have downloaded and installed Couchbase, if you go to the Couchbase web console, you'll see a XDCR tab. If you go to the XDCR page, all you need to do is set the cluster reference for the clusters to know each other, and then you set up the replication. It's so essentially a two-step process, right? There are other things you can do on the XDCR page. For example, you can use our advanced settings for performance tuning. You can do some. There are some. There's a pause resume for if you want to pause the replication and resume the replication, and also there's monitoring stats. Like if you go to our monitoring page, you'll see a bunch of stats for XDCR. For if you want to troubleshoot your XDCR application, right? So which is all provided in the admin console, and we also have it in the REST API. So it's very simple yet powerful in terms of administration, right? Consistent high performance. So XDCR in Couchbase is memory to memory. When I say memory to memory, what that means is like these node on the source cluster, right? So any updates coming to the source node on the source cluster, all of them will be put to the replication queue and sent to the other cluster, right? So it's basically it happens from memory to memory. The performance is basically dependent on your network speed itself, right? Depending on your network speed, the performance of XDCR will be that better. So in some sense, it's basically a highly performant, right? So that's the thing which Dong is going to talk about when he did the testing for the XDCR. In terms of scalability, when you add more capacity to the source cluster or the destination cluster, the XDCR is topology aware, which means that when you add more, when you change any topology in the source or destination cluster, XDCR, you don't have to do anything else. Basically, XDCR will automatically re-establishes the connection, and it's all taken care, right? So as a user, you don't have to do anything there. And it's also basically, if you have the topology between the source and the destination can be totally different. You can have a 10 node cluster in the source, and you can have only 2 node cluster in the destination. It's still fine, right? One another capability of XDCR is the multi-data center active deployment, which is you can have 2 clusters talking to each other, like bi-directional replication between them. And the application can basically do a read and write to both the clusters, right? So you can have basically active deployment itself, right? So that is possible with the XDCR. As I said in the beginning, so it can be used for disaster recovery. If you want to use set up a backup cluster or a standby cluster, You can use XDCR if you want to do a geo distribution, or if you want to use it as an availability solution. In case if the master cluster goes down, I want to automatically switch to the remote cluster, you can use it for availability solution. Sorry, yeah, question?
So you were talking about doing a 10 node to a 2 node connection.
Yes.
Do you have to have your ACLs open across your pipe to both of those? Do all 10 have connections to both nodes on the other side?
That's a good question. The question is, like, do you need to have the ACL open between the source, the two clusters? The answer is yes, because you set up the replication stream between the source nodes and the destination node. They need to talk to each other, so you need to open the ACLs between them.
And the virtual map goes between the two, so it's
Yep.
just like a regular smart client.
Yes, exactly. Yeah. Sorry.
The future releases of Couchbase,
Yep.
are you going to allow replication to power for any new bucket you create, or you still have to configure a bucket every time a new bucket is created for XDCR? That's question number one.
So can you repeat that question?
So replication is not at the, lack of a better term, instance level. It's at a bucket level.
At the bucket level, correct?
So today I have 2 buckets.
Mm-hmm.
Tomorrow I have 4.
Yes.
When that happens, I have to set up XDCR again for that bucket.
Right.
Although the reference has already been established,
Right.
you still have to do that.
Okay.
In future releases, are you going to make it transparent in the number of new buckets that are going to be created in the console? Or
Okay.
That's
Okay.
one question.
Sure.
The second question is today you cannot replicate materialized views.
That's a good question. Yep. Mhm.
In the roadmap, is that in the roadmap that you can replicate views?
Okay, so good question. So I'll first take the first one. So the question is, if you as a user, when you create more buckets in the cluster, will they automatically get replicated, right? So we have this a capability of, bucket in Couchbase is similar to database, right? So setting up a replication, and it's granular on a bucket level. So you can basically say that for this bucket, I want to replicate. We also have filtering capability if you want to basically filter the data from the same bucket. But setting up a replication, like, there's a lot of things involved, right? So you have to basically know that when you set up a replication, you have to size the cluster properly. You need to have the CPUs. You need to have the capacity to handle it. So it's not an automated process in the sense, like, you setting up, as I said, setting up the XDCR itself is a two-step process. It's like you set up the cluster reference once. If you adding the new replication is like a one-step process, right? So it's not automated, but the idea is, like, it's so simple to create it. If you want to replicate the data, it's just a one click of a button to replicate the bucket to the other cluster. Second one, replicating the views. We didn't have that in the roadmap. I think it's a good point. I think I will take it offline. I'll talk to you about adding it to the roadmap. I think that's a good idea. So, on this slide, I want to talk about, we have been doing a continuous innovation in the XDCR. So from the point when we introduced it in XDCR in 2.0, we have been adding new features. We have been adding new capabilities, also performance improvement. And there's a new release coming up shortly. So we did the DP of 4.6. There's a new, so we have a timestamp based conflict resolution, which gives you, if you have a bi-directional replication between the clusters, and if you want to have a global ordering, and if you want to have the timestamp based last write win capability, then that's the thing which is coming up in the 4.6 release, right? Awesome. Thank you. So I don't want to spend more time talking about XDCR. I think the goal of this presentation was to talk about benchmarking XDCR ring topology at PayPal. Before I hand it over, so I just want to talk about the PayPal has been using a Couchbase for many of the use cases. I think the global profiles, globally distributed profile store, session store, I think they are expanding into many more use cases, the mission critical applications, and that's why they wanted to do this benchmark to validate the XDCR, right? And so I'll bring the Dong to the floor. Right. Thank you.
Everybody hear me? Turn it up. All right, turn it up. All right. Test. No? Okay. Thanks. All right. So thanks for coming. And today we are going to present the data that we collected during the process of benchmarking the Couchbase XDCR in a ring topology architecture. So I'll go over a few slides covering those agendas. First, I'll describe the little bit background about our company, myself, and then we'll go over the background on the multi-data center bidirectional ring replication benchmark. And also we'll cover the benchmark methodology and results and our tuning efforts on those. So hopefully after this talk, you can benefit from the results that we obtained. First of all, I think everybody is very familiar about our company. We are a leading technology platform provider in participating in the digital economy, as everybody attended yesterday's keynotes. We process billions of dollars of transactions online, and the number of active users is growing rapidly. About myself, I was trained as a PhD in biochemistry, but later on changed my career. And have been working on the database technologies for the past 18 years. For the last 10 years, I spent my tenure at PayPal, and currently leading the PayPal's NoSQL engineering efforts. So to go to our multi-data center benchmarking content, here is the purpose. We want to do a benchmark to answer one question. So when we deploy the multiple Couchbase clusters in multiple data centers, we have two choices about the topology. One is using the ring architecture. The other is using a mesh architecture. So those different architectures are depicted at the bottom of the slide. If you can take a look at the left side of the slide at the bottom, this is the ring architecture, right? So in that picture, we have 4 clusters. Each cluster is having 2 downstream targets for it to send the data to. So overall, we have 8 XDCR streams among those 4 clusters. On the right side, that is the mesh deployment architecture. Mesh means everyone talking to everybody else. So in addition to those ring architecture deployed XDCR streams, there are some additional streams being involved, mainly the ones in the center of those of the picture, right? So if you count the number of streams for a 4 cluster, we have 12 streams. So if you increase the number of the clusters in multiple data centers from 4 to 5, and then the difference between a ring versus a mesh will be even bigger. So our requirement is to deploy that to multiple data centers, and the data replication has to be happening among those multiple clusters in a bidirectional way. And our active traffic is directed to all of those data centers. So that's the requirement, and those are the 2 choices for the deployment patterns. So we did this benchmark to try to answer the question, is a ring architecture a valid approach for us? So that's what the data I'm going to show you today. Here is the comparison of the ring versus the mesh in terms of the number of XDCR streams. So if you do the math, for the ring deployment architecture, for n number of clusters, it involves 2 times n number of XDCR streams. For the mesh, it would be n times n minus 1. So the more of the clusters involved, the larger of the difference. Our benchmark to test the ring deployment architecture involves 4 data centers. First, I'll describe the benchmark environment. Next, I'll describe the benchmark procedure. And I'll describe the benchmark data collection process, processing data, and do the results in the end. The environment we use involves using the bare metal Dell PowerEdge FC630 hardwares. So each of the machine has 20 cores with a hyper-thread CPUs at 2.6 gigahertz. And each machine has more than 300 gigabytes of the RAM available to it, with a 10 gigabits network card, and with 2 terabytes of the SSD storage. We use 8 of those nodes to form a cluster, and each data center have a cluster, so we total employ 4 times 8, 32 nodes. All of those bare metal machines run the Red Hat Linux 6.6, and we use the Couchbase 4.1.1, running the XDCR without SSL. So we also use the benchmark tool of YCSB. It provides the Couchbase binding, and the version of the YCSB we use is 0.9.0. In addition to the YCSB tool, we also developed our own data replication monitoring custom tool to monitor how the data are replicated with what kind of latency among those different data centers. So it's a standard Python program using the Couchbase Python SDK. So that's the environment. And here is these components. So it's kind of a lot of arrows in the graph, but I'll try my best to explain to you. So basically, those orange lines separate those different regions. So as I mentioned before, we have 4 data centers, right? So each data center runs a similar set of machines. Okay, let's take an example here on this right side. So in this data center, we have a group of machines running Red Hat Linux, Couchbase. That's the Couchbase cluster. And it's talking to 2 clusters in the ring architecture. And we have a group of machines running the YCSB clients, and also we have 1 machine running our custom replication monitoring client. So those are the machines that involved in each data center. It's the same across all the 4 data centers. And one thing I want to point out is that there are 3 data centers. They are in the same region, geographic region. So the network latency among them is very small. And 1 data center is in a remote location. So the network latency from this particular data center to all the other 3 is large. So there is asymmetric characteristics here in terms of the neighboring effect, right? So if you choose the top one, the top data center, both of its XDCR targets are very close to it. But if you choose the bottom one, both of its XDCR targets are remote. They have higher network latency. So this is a key point that later on it will show into our results. So I just want to point this out to you. In terms of the benchmark procedure, we do the cluster configuration. We run in parallel the YCSB traffic generation, in addition to our replication monitoring program. After each of these testing cycle, we collect the data, process them, and analyze them, and then go through multiple iterations. So we collected a lot of graphs, and I'll show you some results today. The Couchbase configuration is a typical configuration. We try to keep it to use as much default settings as possible. In terms of the cluster configuration, we use the standard best practice on the operating system level, such as turning off the THP, setting up the swapping correctly, and we use the XDCR setup, which is very easy to recreate using the REST APIs. For the bucket configuration, we create the buckets at the standard Couchbase type. And for the memory allocation, this is people-specific. We only allocated 240 gigabytes per cluster, even though each node is much more capable to providing more RAMs to the cluster. The reason we choose that is to give us more closer mimicking to our real situation that we do not have unlimited RAMs available to us. So basically, we want to try to keep some of the data on the disk and some of the data in memory. Replica number is set to 1, and it is using the value ejection. Disk I/O priority is set by default, and the auto compaction is configured at the 30% level threshold. So it will always run in the background whenever you need it. And the flush is enabled. So that's the Couchbase configuration. Workloads. We use 2 workloads from YCSB that is provided. One is workload A. It is a 100% write workload. The procedure we use is we drop the XDCR stream, we flush the bucket to get the bucket cleared, and then we run the loading, create the XDCR stream, and we run the loading. At the same time, we run the monitoring traffic program. So that's going through just one cycle, and we repeat that with different testing conditions. The other workload is the workload B. The workload B is a read-intensive workload. It's consisting of 95% read, 5% write, which is update. And we preload 200 million documents into the cluster, which will result in more than 400 gigabytes of data on disk, and 200 gigabytes of the data would be in the memory. So that's kind of a balance between the physical on disk and versus what can be kept in the memory. And then we run the YCSB workload from various number of clients, hosts, and we run the XDCR monitoring traffic as well. So that's the 2 benchmarking workloads. In terms of the data collection, we collect the data generated from the YCSB, as you can see on the slide. We generate the insert overall throughput, average latency, minimum, maximum latency numbers. We collect all of those from individual instances of the running, and we summarize them together, either do an aggregation or do average, max statistics on those. For the XDCR latency monitoring, we use our custom tool, as I mentioned earlier. What it does is that it will insert a document with a known key to its local data center, and then immediately monitors the arrival of the same document to those other data centers right after. So then we keep track of the timing and get the XDCR latency.
Could you just share a little bit more about how you're validating the data between the data centers?
Validate the data?
Yeah, isn't that what you just said the second part?
That's the monitoring the arrival of the data to, from one data center to the other data center. Because we know the document key, so we can do a query immediately after we receive the acknowledgement of the insert from the primary data center and check the arrival of that document in the other data centers. If we cannot see it, we immediately loop it again to try to access the same document again until we see it. And then after we see the document, we keep track of the timing so we know, okay, when this get finished the insertion and when we can see the document in the other data center. So that gave us the XDCR latency. Yes? Yeah.
You have 20 client system.
Uh-huh.
You write into the primary data center.
Right.
You go to the query to the other data center.
Yep.
Question is, from the client which is on one data center, you use the same machine to go to the cross data center?
Yeah, exactly. We use the same machine. It's the same machine. It generates the inserts and immediately checks the arrival of the same document it's inserted from the other data centers.
Two more question. The YCSB workload generator is something you got from Couchbase or? And the second one is, what is the tool that you use to gather that metric in the previous slide?
Okay, so the first question is about YCSB workload generator. We use the YCSB Couchbase binding.
Yeah.
So it has the driver's built-in logic there. So it will generate the documents based on your specifications, such as the document size. And it creates one, it inserts into the bucket that you specify. So in that regard, we don't have any customization.
Yeah, it's available on the, it's publicly available, and we can add the links to the document.
Yeah. Second question is about how we generate, how we collect those metrics, right?
Previous slide, I saw some metrics. Very interesting. What do you use to get that?
These metrics? Yeah, this metrics is generated by YCSB after it's running. It's in a format of a log file. Okay, so in addition to those information, we also collect the Couchbase generated metrics. We use the REST API call to call the endpoints and gather those different metrics at the end of each run. And we do analysis on those and do graphs on those as well. In terms of the processing, the sample window we use is a 2-minute sample window out of a 5-minute run. We try to take the middle portion that is showing a more static, steady state. And for the data, if it's aggregatable, we will do the sum of those, such as the throughput. If it's not aggregatable, we do the average, mean, max of them. The data graphs are generated by using the Python matplotlib library with the pandas. Okay, so now let's go to the details about the benchmark results. So first, I want to present the 100% right benchmark results. So in this benchmark, we have 4 clusters, as I mentioned before. Right? They are bi-directionally replicated. The first result we got is about the workload throughput. This is to the perspective of the YCSB client. So the x-axis is the number of threads we ran. The y-axis is the number of documents per second it can process. So as you can see, it can scale when we increase the number of the threads. On the left side is the overall throughput. On the right side is the insert failures received by the clients. So even though we can see that the throughput get increased when we increase the number of the threads, but we started to see the errors from the client side when we reach the 80 level on the right side. So this is probably related to the memory limitation when we assign to the bucket. So if you can allocate more of the memory to the bucket, you will probably see a later onset of those errors, at least.
Just wanted to clarify that, the goal of this test was not to do the performance benchmark. It was more of validation of XDCR. And as Dong said, so based on their configuration, they had set the memory quota. So you saw the results here are for the configuration what Dong has for his cluster, right? So you'd see different results when you have a different configuration. So it's not a performance benchmark or you won't see the same results on your cluster.
Yeah, basically the goal is not to chase the maximum, absolute maximum. It is to validate our topology decisions. So the maximum throughput we can see without errors from the left side is about 340K per second. So that's a number for the 100% right workload. So now we move to this P99 max latency to the perspective of the YCSB client. So if you take a look at the left side of the graph, it shows the latency levels for all the inserts with the 99 percentile. With the increased number of the threads, we see those latencies reach to like a millisecond level. So that's still a good number for the application latency. However, on the right side, if you see that when we increase the number of threads, the maximum latency to the perspective of the client get increased once you above a threshold. So basically, this tells you a comfortable zone of the system that you can get a best application latency. Now let's move to the XDCR latency. So we covered the application throughput. We covered the application latency. Now we talk about XDCR, the data replicated from one data center to the other, right? So here is a graph shows to each prospective data center how the data get arrived to the other data centers. So in each of these subgraphs, is the data generated from the local data center. Remember earlier I talked 4 data centers, right? So let's take one example of the top left. This is a data center that has 2 XDCR targets to the same region. So the network latency is fast within the same region. However, the 4th data center has a higher network latency. So that's why we see that the blue line here is inserts. It inserts quickly. And the red and the green are having a lower latency. But this kind of the bluish color on the top, that is the one to the remote data center, which has the farthest distance from the local region. So the similar pattern you can see is all these other 3 data centers. And quite interestingly here in the last one, because that one is the remote data center, every other data center is far away from it. So all the 3 data centers XDCR latency get pushed to the same level. So that means that it is a network latency driven XDCR latency behavior that we have observed.
Are all 4 of those the same scale?
Those 4 is, yes. The top is 1 second. The lower is 0. But here there's a -1. So you just ignore this -1. The 0 starts here. So it's not a log format. It's a linear format, y-axis. It's the same scale.
Doesn't look like the top right and the bottom right are the same scale. It goes up to 100 on the bottom right, I think. It's really hard to see.
Yeah, it's the ticks. It's up to a second level.
No, but you look at the y-axis on the top right. I see 0, 10, 20, 30, 40, 50, 60, 70. I'm assuming.
Yeah. Right, so those are the ticks. Yeah, so those are the ticks. So if you just get those numbers, they are roughly the same level at like from the left. It's 30 to 50 milliseconds. Yep. So if we increase the number of the threads and increase the traffic, so what we have seen is that all the latencies get pushed up. But the ones get affected the earliest is the one that is the most farther data center. So again, is that with the increased throughput demand, the distant data center got affected first. And when you increase the number of threads again, you will see the local data centers get pushed up as well. And if you look at the lower row on the right side, all the 3 data centers XDCR latency get pushed to the top at 1 second level. So that means each data center is reacting differently based on its neighboring effect, based on the network latency, right? But the remote data center got affected first. If we take a graph of the Couchbase internal metrics for the DCP XDCR items remaining, this reflects how many of those items are being put on the queue, ready to be replicated. If we plot those numbers against the number of threads, what we have seen is that the accumulation point for the XDCR traffic happens much earlier than the client error onset, and also happens much earlier before we reach the maximum of the overall throughput. Because the asynchronized feature of this XDCR, once document arrives to your local data center, they are put on the queue to be shipped to the remote data center. So those 2 different processes reach their bottlenecks at different times. So now let's move to the 95% read use case. Similar for data center, active. If we do the workload throughput from the YCSB perspective, what we have seen is that with the mixed workload, with the read intensive, usage type, we reach this overall throughput much higher than the insert only. So here we can reach 3 million, 4 million per second. Remember before it's only less than 500,000 per second. Yeah?
On the previous slide, earlier slide, and the one which shows the EP latency.
Yeah.
So maybe Anil might talk about it. Question was more, if you have a queue, the XDCR, the items are put in a queue for XDCR. The queues are two different queues, one for the local XDCR, another one for distant XDCR. Based on that, they will create, I'm answering now, I'm kind of thinking through.
Yeah.
But they will have a different backlog based on the latency.
That is correct. So there is a
Different queues will maintain different backlog.
that is correct. So there is a internal queue for intra-replication, and there is a the another queue for XDCR.
Is that queue configurable?
No, that's all. Sorry. So no, that's not configurable. So that's part of the XDC Couchbase.
Okay. So let's quickly go through this 95% read workload. This has a higher throughput, and also the latency level is at millisecond level as well for both reads and writes. If we talk about the maximum latency, they have the same behavior as showing a comfortable zoom. And if we talk about the XDCR latency among those 4 data centers, we see a very similar behavior as we saw for this insert-only workload. So with less workload, they have a nice band showing only the remote data center having the delay. With the increased workload, it gets pushed up. With more, it gets pushed more. And for the remote data center, it reached to a 400, 600 millisecond level. And in terms of the XDCR backlog for these XDCR items remaining, they show a different profile as well for the accumulation. So the onset of this follows their network position. We also did a comparison between the different topologies. The one I showed you earlier with the graphs is all 4 data center, 4 active. So we also did a comparison between 4 data center, only 1 active, versus 4 data center, 2 active, versus 4 data center, all 4 active. So we can get some idea about what kind of scalability we can get from those different arrangements. So this is a summarization about the throughput. With 100% workload, those different arrangements, we do not see much of the difference. For the read-intensive workload, we see a 1.8 scalability if we use 4 data centers, 4 active. The reason for those is because that the client traffic needs to be translated into the KV traffic. So if you have multiple data centers all taking the traffic, it's the same as only 1 data center taking the client traffic. The end result for the overall KV traffic is still the same. Application latency versus traffic pattern. We see very good application latency with all of those different topologies. For the data replication latency for the traffic pattern, we see that with 100% write, the close data centers, they have much lower latency. And the far data centers, they can reach 100 millisecond, 200 millisecond level. Even though if you do a pin time between those data centers, it's only 15 milliseconds. So there appears that there is an application effect for the data replication latency. And the write-intensive latency is higher than the read-intensive workload. So to tune this throughput, what we have done is that we used the later on YCSB release and changed different configurations regarding to the XDCR configuration. One is the nozzle increase. By default, each one has only 2 nozzles available, which means do the parallel shipping of the XDCR traffic. We increase that from 2 to 4. The other tuning aspects includes increasing the batch size or increasing the optimization threshold to reduce the round trips. So we did all of those. And I just want to show you one result, which is the nozzle increase. So what we found is that by increasing the nozzle from 2 to 4, we see the most benefit of increasing the throughput of the XDCR. So in the graph, you can see that from the left side, that is with 4 nozzles. On the right side, that is with 2 nozzles. Both of them generates similar throughput at more than 300,000 per second, and with the average latency of 0.2 milliseconds. However, if you take a look at the XDCR latency, on the left side, it's much cleaner.
And what are nozzles in reference to XDCR queues?
Yeah, so the nozzles are like the replication streams, right? And again, if you have more horsepower, like if you have the machine has more CPUs, you can increase the nozzles from 2 to 16 or to a much higher number. Yeah, exactly, right? So we can drain the XDCR queue much faster.
Okay.
And these are configurable through the REST API?
Yes, it is. So you can make an API call and change that.
You also said that nozzle count made the most difference. Why do you say that the other option? Like, did you test each one of the settings independently and then found that the nozzle?
The general practice is to change both nozzles to the receive and send at the same time. So they make a symmetrical.
So the nozzles in XDCR in Couchbase level in the YCSB?
It's in the Couchbase, within the Couchbase itself.
Yeah. So when I was talking about the on the console, so we have XDCR page. So there's advanced settings for each replication you create. You have advanced settings. You can basically use this advanced settings to change the different parameters. And nozzle is one of the parameter, right? So you can change to fine tune your replication. So if your machine has more CPUs, you can add more nozzles to your replication.
Okay. Yeah. So the other considerations for a higher XDCR throughput. So we can, of course, increase the RAM allocation for the bucket. So the more RAM, the better performance. Or we can use a faster disk. So if you are using spindles, you can change the SSD. That will certainly improve the XDCR. Or you can upgrade to the later versions of the Couchbase, which has optimizations built in or improved, right? So to summarize that, so we conclude that the Couchbase multi-data center active-active deployment pattern provides a very high availability and scalability for us. And currently, we are deploying this architecture in production. And the scalability is more dependent on your use case. So read-intensive use cases tend to benefit better with multiple data centers. And XDCR latency is largely affected by the network latency. It can be much higher than the network ping time. And the geographic located data centers, they have different behavior. For those group of data centers which are close to each other, they tend to have data to be consistent with each other, better than the ones far away from each other. Yes. And also, the XDCR throughput versus the overall application throughput, they maxed out with a different profile because the asynchronous feature of it. So they move independently. So very likely, before even you reach the max of the client-side throughput, you probably will start to see the XDCR lagging already. So that's the take-home message that I want to share with you today. Thank you very much.
So yeah, so if you have any questions, we can take the questions now.
Just wondering, I know this is based on like on the ring-based kind of thing. What is on the mesh kind of, that architectures you guys have finding or something?
Yeah, so the question is about all the data we presented is based on the ring architecture. We did not present anything about mesh. Basically, we stopped at here because this architecture clearly satisfies our need. And on paper, there are more and more XDCR streams involved if you use more data centers. And each XDCR stream, if you attended sessions from yesterday, requires one extra CPU to be allocated for this. So certainly we know that it will be more resource intensive for it. Yeah.
When you run a value into cluster number 1, it gets replicated to 2, then to 3, then to 4. Does it eventually come back to number 1?
Well, actually, the path is not just like from 1 to 2 to 3 to 4. If you have bidirectional ring, if you see 1 to 2, 2 could go 3, right? At the same time, 1 could go 4, and 4 could go 3. So depending on who arrives the first from which path, the end result on 3 could be coming from either direction.
Right. So if the key is already there on the cluster, so it won't basically even write it. So for example, if the
You have to check to make sure it's not different?
yeah, so that's the thing. So it will do a so before we replicate, we do a set with meta check. So we check whether the key already exists. If the key already exists, then we don't even replicate the data. So that's an optimization, basically.
Okay.
How complicated was this data which you were testing with?
The question is about the complexity of the data we tested. The test data is generated by the YCSB. We only specify the document size. So if you look at the internal, it has like 10 fields, each field with a certain bytes in it. If you specify like a 1 kilobyte per document, it will spread among those 10 fields, each one with 100 bytes. And they're all random. So.
Any other questions?
One more question about
Yeah.
this DCP, which you said in 4.5 XDR
Yeah.
has improved. What is this DCP do different than
Okay.
existing architecture for XDR?
Right. So DCP is not any different. So it's so that's the streaming protocol we introduced in 3.0, right? So we had a tap protocol which was a push-based protocol in the past. We replaced the tap with the DCP, which is now the streaming protocol within Couchbase, right? So all the any updated mutations will basically come in the DCP stream, which will then get into the XDCR queue or the internal queue for getting replicated. And when Dong was talking about optimizations, we have been constantly adding performance improvements for the DCP protocol. So with the new versions, you'll basically see a better performance with the DCP and XDCR.
All right, thank you.
Go ahead. Yes.
So, let's say if we have multiple clusters with XDCR, right?
Yeah.
Each cluster would have its own working set, right?
Yes.
So when the replication actually happens, right, how do you take a call like what all data elements need to be flushed out, like what gets priority?
So the question is like if you have two clusters, right, and then you have and each cluster has a different working set, right? So basically you have set the data is going to a bucket and you have set the bi-directional application. I'm assuming the bi-direction. The reason you set up this way is basically you want to have the users of this cluster will go to the cluster A, the users of the other cluster will go to cluster B, for example, right? So if we have a bi-directional, if the key is only goes to the particular cluster, then all you're doing is you're synchronizing the two buckets, two clusters at the same time. So you want to have the data availability, right? So there's no conflict in that case. Let's say if you update the key on both the clusters, right, then there's a chance of conflict, and we have a conflict resolutions, which I was talking about earlier. So in the past, we have a revision-based conflict, which is it looks at number of revisions, number of updates happen to this particular key. Based on that, it resolves the conflict. Now in the 4.6, we have a timestamp-based conflict resolution, which will look at the timestamp when this conflict arrived and pick the winner based on that.
So in this in the
Yes.
existing older 4.5 version,
Right.
this conflict
Yep.
which is, you kind of have a solution by checking how many the most update state.
Correct,
based on
correct.
the key, right?
Yes.
Is this work out very well in a very heavy transactional system?
So,
outside?
yeah, so in most of the use cases where we also have recommendations for that, but so in most of the use cases we have seen that if the key does not get updated on the same time between the two clusters, then the revision-based conflict resolution works works correctly. But what we started increasingly saying is, like, we started saying globally distributed database where the application can write the data to the two clusters. So in that case, the conflict can happen. So we wanted to have global ordering in some sense. So we wanted to have the timestamp for that, so that when we look at the timestamp, we pick the winner based on the one which is last updated, right? So that feature is coming in the 4.6.
Okay.
Yeah.
And when the conflict happens,
Yes.
let's say it happens,
Yeah.
then is there XDR breaks or stops?
No, so XDCR keeps going on. So the conflict happens. Usually the target is where the conflict resolution will happen. And the conflict resolution mechanism itself is in the core engine part, where it looks at the conflict and then resolves the conflict. Whereas XDCRs keep on going, it logs the message, it does all the stuff, but the replication is still going on. Yeah. Cool. Yeah.
When you increase the nozzles from 2 to 4, does that further degrade the application throughput and latency?
No.
If you decrease it to 1, would that improve the application?
No, it has a separate effect. So it does not have an effect on the application latency or throughput by changing the nozzles. The nozzle is only a tuning point for the XDCR, because XDCR behaves differently than the application throughput or latency. So you can finish your insert to the Couchbase bucket, but simply the document is not replicated.
So in some sense, it's like a sizing exercise, right? So you want to know, if the machine has 4 cores versus 8 cores, how much capacity it has, right? So depending on number of cores, you can definitely increase more nozzles, and then the replication speed will be much faster, right? So it's basically a sizing exercise. Yeah.
Can you talk a little bit about what happens when there's a network partition between the data centers?
Mm-hmm.
What happens to XDCR, and then do you need to account for that by tuning some of the queue parameters and other things?
That's a good question. So the question is, when there's a network partition, how does the XDCR behave, right? So we have checkpointing, and that is also configurable, right? So we do a regular checkpointing, and that so the default is set to 10 minutes. So every 10 minutes we take a checkpoint on the source cluster. So let's say if there's a network partition and the XDCR fails, so and it's all automated in the sense, like the XDCR will try to restart the connection. And when it restarts the connection, it goes back to the old checkpoint and start from there, right? So it knows where it left off, and from there it starts catching up, right?
But then if there's a huge backlog, do you need to tune certain things?
Yeah, so it's again, so in that case the latency will be higher, but yeah, again in that case, if you have more nozzles, you can basically fine tune your replication, yes. Right. Good, all right, thank you so much, guys.
Thank you.